If humans are going to stay on the moon, it won't be because of rockets. It will be because of one dark crater near the South Pole. The Artemis 2 crew just returned home, and the images of Earth from space reminded everyone why we explore in the first place. They're beautiful. They're emotional. But if you want to understand what lunar missions will actually look like over the next 10 years, don't look at Earth. Look at the moon's South Pole. Because that's where the moon stops being a destination and starts becoming infrastructure. Near the South Pole sits Shackleton Crater. It's deep, steep-walled and surrounded by sharp ridges where sunlight behaves very differently than anywhere else on the moon. Inside and around this region are permanently shadowed areas, places where sunlight almost never reaches. Temperatures there stay so low that water ice can survive for extremely long periods. Scientists call these regions cold traps. That's why Shackleton keeps appearing in mission plans and landing studies. Not because it looks dramatic, but because it could make long-term operations possible. Water ice isn't just about drinking water. It supports life support systems. It can be split into oxygen and hydrogen, and those are the same ingredients used for rocket propellant. Without local water, every mission depends entirely on launches from Earth. With it, the moon can begin to support itself. That's the difference between short visits and sustained presence. And that's why the South Pole matters. This isn't just a NASA story. China's CHANG'E 7 mission is designed specifically for the Lunar South Pole. Public descriptions show it includes an orbiter, a lander, a rover, and a small hopping probe, built to reach terrain traditional rovers struggle with, especially near dark, uneven regions. Based on current reporting, CHANG'E 7 is moving toward launch preparations for the second half of 2026. This isn't about symbolism, it's about capability. CHANG'E 7 is built to measure the South Pole environment and directly investigate potential water ice in places where power is limited and conditions are extreme. The South Pole is one of the hardest places humans have ever tried to work. The moon's tilt is small, so the sun never rises high in the sky. Instead of day and night, you get something closer to an endless sunrise. Long shadows stretch across the surface. Crater interiors remain dark. Ridges and crater rims can stay illuminated for long periods. Power becomes geography. If you land in sunlight, solar power is possible. If you land in shadow, everything changes. Batteries, thermal control, survival in extreme cold. People talk about peaks of eternal light, but the reality is more precise. There are no spots that are perfectly lit all year. There are locations with very high illumination, and those locations make sustained operations far more realistic. NASA isn't betting everything on one exact landing point. Using data from the Lunar Reconnaissance Orbiter, NASA has identified multiple candidate landing regions near the South Pole. These regions were selected based on terrain safety, communications with Earth, and lighting conditions. They're regions, not dots on a map. Launch timing, sun angle, and surface conditions all matter. Flexibility is essential. So when people say NASA is landing at Shackleton, the accurate version is this. Shackleton is part of a broader operational landscape NASA is studying carefully. If water is the prize, landing is the gatekeeper. South Pole terrain makes Apollo landing sites look simple. Low sun angles hide rocks and slopes in shadow. Contrast is poor. Hazards are harder to see. NASA's solution isn't pilot instinct, it's technology. For Artemis missions, NASA is targeting landing precision on the order of tens of meters, roughly the size of a football field. That requires hazard detection LiDAR, onboard computers processing terrain in real time, and navigation systems that understand exactly where the spacecraft is relative to the surface. CHANG'E 7 is aiming for similar precision, with publicly stated goals under about 100 meters, a serious technical challenge in terrain like this. This is where missions succeed or fail. Mobility matters just as much as landing. Rovers are careful and reliable, but slow. A hopping probe can potentially cross terrain barriers and reach shadowed regions faster, but every hop adds risk. It's not just a leap of distance, it's a leap between environments that can differ by hundreds of degrees, forcing the hardware to survive extreme thermal cycling. If China's hopping probe performs well, it won't just be a science result, It will be a demonstration of how to reach ice without getting stuck in permanent darkness. That's the South Pole problem in one sentence. No one owns the moon. International agreements make that clear. But in practice, there is competition, not for territory, but for capability. Who can generate power reliably? Who can land precisely? Who can move safely? Who can measure what's really in the cold traps? The first missions that answer those questions will shape standards, partnerships, and the pace of everything that follows. The moon's south pole is difficult, and that's exactly why it matters. Almost no margin for error. The next chapter of lunar exploration won't be decided by speeches or flags. It will be decided by engineering, by systems that last, by precision landings in unforgiving terrain, and by careful work at the edge of permanent darkness. We'll keep tracking the missions, the hardware, and the data as it comes in. Tell us in the comments, what do you think? This is NASA Community News, and this is just the beginning of the South Pole story.